Hello everyone. I decided to go with the UHF antenna design project for today's presentation, and in the next couple of slides I will be going through a detailed explanation of the antenna design, focusing specifically on the dipole and the Yagi aspects that we were assigned in our lab, specifically to the frequency of 450 megahertz. First, what we had to do was we had to select a design from the 4 available antenna designs. The first one is the classic dipole, a simple 2-element antenna known for its balanced radiation pattern. Next, we have the folded dipole, a variation that brings increased impedance and wider bandwidth. Then, the balun folded dipole, which introduces a balun for improved performance, minimizing common mode currents. Lastly, we had the quad antenna, a directional loop forming a square or rectangular shape, renowned for its high gain and focus strength. For my design, I went with the dipole antenna. So first we had to do some calculations. The first thing we had to do is calculate the length of our dipole antenna, which the formula for that is 468 over the frequency. The frequency that we were given was 450 megahertz. I also multiplied that times 12 so that I could get the length in inches, which is about 12.48 inches. I used about 12.5 inches. After that, we had to calculate the element spacing of each side of the dipole. To do that is an easy calculation. We just had to calculate the length divided by 2, which gives us about 6.24 inches, and I used about 6.25. Here's a little image that shows what each of the lengths looks like. And then the next phase of this project was to test the antenna itself. And then as we can see on the picture on the VNA, you see that the reflected loss is negative 0.24 decibels. The standing wave ratio is 1 over 73.62. The impedance itself is 1.74 plus J24.8 ohms. As we can see, the reflected loss indicates a very small amount of reflected power was shown. And the SWR suggests that it's a pretty reasonable impedance match. However, there is still room for improvement. We can definitely tell that there is room for improvement based on the impedance itself. As we can see, it's not super close to 50 ohms, which is the ideal value. And once again, that might be due to user error. And then after we were done testing the dipole antenna by itself, we were asked to create a Yagi antenna using the dipole antenna. As we can see, the calculations are shown here. First, we had to calculate the wavelength, which is going to be about 26.22 inches. And then from there, we use that to calculate the length of each one. So the directive, which is going to be about 11.79 inches, and I used about 11.8 inches. And then after that, I had to calculate the spacing, which is about 3.93 inches, and I went to about 4 inches from the dipole itself. And then after that, we have to calculate the reference length, which gave us about 14.421 inches. I think I rounded up to about 14.5 just to make it easier on cutting out the wire. And then the spacing for that is about 6.5 inches is what I used. And then after that, we move on to testing the Yagi antenna itself. And as we can see, using the Yagi antenna very much improved the results of the dipole antenna. And as we can see, the negative return loss is about negative 0.39 decibels. The SWR is 1 over 44.48. The impedance is 6.14 plus J 42.9 ohms. So as we can see, the return loss indicates a minimal reflected power, which signifies a very well matched Yagi antenna. And we can see that is very much an improvement from the RL of the dipole. which again shows an improved impedance matching. And then a notable enhancement from the dipole is the SWR. As we can see, the SWR was 1 over 73.62, and with the Yagi antenna, it is 1 over 44.48. This indicates that the impedance matching was improved, and a lower SWR is very important for power transfer. And then we can see that the impedance also drastically improved. As we can see that the reactive is 42.9 ohms, and we need to be as close to 50 as we can because that is the ideal value. And then after testing both the Yagi antenna and the dipole antenna, I went ahead and did a performance comparison. So first we'll start off with the return loss. So for the dipole, it was a return loss of negative 0.24 decibels, and for the Yagi, it was a return loss of negative 0.39 decibels. The Yagi antenna had a lower return loss, which shows an improved impedance matching and a reduced reflected power, which is very important for antennas to get a clear reading. After that, we had to compare the SWR. For the dipole, it was 1 over 73.62, and for the Yagi, it was 1 over 44.48. The Yagi antenna showed a reduction in the SWR compared to the dipole, which again further enhances the performance in transmitting and receiving signals between both antennas, or the difference in both antennas. Then after that, we had impedance. The dipole's impedance was 1.74 plus J 24.8, while the Yagi's was 6.14 plus J 42.9. As we can see, there's a drastic change between the dipole's impedance versus the Yagi's impedance. The Yagi's impedance was closer to the ideal impedance of 50 ohms, which is what most antennas' standard value is. And the closer to the target value we get, it's going to be crucial for effective communication that we receive from the antenna. After that, I did an overall performance between the two, which is going to be that the Yagi antenna definitely helped clear up any values that we could get from the dipole itself. The dipole by itself can get pretty close to accurate results, but with the Yagi antenna, we had a more clear, accurate results with the values, and it was closer to that impedance value of 50 ohms. And then again, this would work with any of the other designs that we had between the folded dipole, the Volin dipole, and the quad. I will say when I first did this lab, I mistakenly used the wrong calculations, which is why when I first did the lab, my values were very much out of whack and I could not really see a difference. However, going through this presentation, I was able to see how it was supposed to go, and these numbers make a lot more sense and are closer to what we've seen in both labs and lectures as well. So I will say that this presentation has definitely helped me understand each of the antennas a little bit better now. And I thank y'all for your time. Hope you'll have a nice day.